So good morning students. Once again, in this class, I'm going to discuss about a concept called race around condition in ZK flip-flop. What is race around condition in ZK flip-flop and how it can be overcome in ZK flip-flop. So these things I'm going to discuss in this lecture. So race around condition occurs in ZK flip-flop when both inputs of JK flip-flop, that is J equal to 1 and A equal to 1. There is a possibility for existence of this race around condition in ZK flip-flop is whenever both the inputs of flip-flop is equal to 1. If the width of the clock pulse TP is too long and the propagation delay of the flip-flop is less, for this condition, this race around condition was occurred. What is actually race around condition? The state of the flip-flop will keep on changing from 0 to 1 and 1 to 0 continuously. That means we are not getting a fixed output for a complete clock pulse. The output of flip-flop is continuously shifting between 0 and 1 and 1 and 0. So because of that, the output of the flip-flop is not certain, it is uncertain. This particular phenomenon is called a race around condition. This race around condition can be eliminated in ZK flip-flop by using two different methods. One method is by using edge triggering notation, and second one is by using master-slave configuration. So here our idea is either you have to reduce the clock pulse width, that is a TP, is not too long, it should be less, or you should increase the propagation delay of flip-flop, that is it is not less, it should be more. We achieved either of these two, we can overcome this race around condition. That is our idea in these two methods. So this is the JK flip-flop. Here I was using positive triggering. It is not edge triggering. If you have an edge triggering internal to the block, we have arrowhead. Here there is no such arrowhead here, so that here your flip-flop can follow level triggering, which is a positive level triggering. So these are the J and K inputs. Outputs are this is a QT1 bar, QT1, QT plus 1, and this is QT1 plus bar. Uncomplement output and then complement output. This is the characteristic table of your ZK flip-flop. So when both the flip-flop inputs, that is J equal to 1, K equal to 1, QT plus 1 becomes QT bar and QT plus 1 bar is equal to QT. QT plus 1 is basically next state and QT is nothing but a present state. So this state value is continuously shifting. Always it should be complements. As long as this clock pulse is high and the propagation delay of this whole flip-flop is less. This is, we know that the logic diagram of our ZK flip-flop. The outputs are fed back to the input. This is the main reason why you have a race around condition was occurred in this JK flip-flop. The output is fed back to the input. So see here, Q bar is connected to here and Q is connected to here, feedback. The total propagation delay of this circuit is less than the width of your clock pulse. That it is better understood by taking a waveform. See here, my flip-flop is positive level triggered, so that this is a positive level of a clock. That means your flip-flop can accept this J and K inputs only at the positive level of a clock. Based on that J and K inputs, it should be produces an output. Once K is equal to 0, output is 0, but J is equal to 1, output is 1. If both are 0, 0, it will maintain a previous stage as it is. If it is both are 1, 1, the output should be complementing each other. That is, it should be toggles. If you remember that, my clock pulse width is this much duration. Let it be, you can assume, friends, this whole duration is equal to some 80 seconds. The propagation delay of this circuit is just only 20 seconds. The width of the clock pulse is 80 seconds, but the propagation delay of your circuit is just only 20 seconds. Then what happens? See here, friends, J0, K is 1. I am already told you that my K value output Q value is 0. Once K value is 1, so this duration it is equal to 0. And thereafter K value is 0. At the same time, J value also 0. It will maintain a previous stage as it is, so that in this duration your Q value is 0. But later J becomes 1 from 0. But K is continuously 0. Once J is 1, your Q output is 1. But here onwards, what happens is both J and K are 1s. And here the clock edge was finishes. This duration, what happens is the state of my flip-flop is continuously shifting between 1 and 0, 1 and 0, 1 and 0, 1 and 0. I'm already told you the duration of this is equivalent to some 80 nanoseconds. The propagation delay of your circuit is 20 nanoseconds. Then the number of times we are changing the output at a Q is 4 times. So output is not a stable like previous case. It was an uncertain case. The output is not a fixed. So this particular case we are calling as a race around condition. That means the race was happened between 1 and 0, 1 and 0, 1 and 0. So that's why it is called a race around condition. It can be overcome, I'm already told you, by using edge triggering notation or by using master slave configuration. In edge triggering notation, what we do is, if the clock is high for a time interval is less than propagation delay of flip-flop, then race around condition can be eliminated. This is done by using edge triggering rather than using level triggering. That means here my intention is, instead of taking this much duration of clock pulse, if I go and take only the flip-flop inputs acceptance only at this edge or at this edge, that means the duration of this pulse width is drastically reduces. Then automatically the race around condition was not occurred because I consider these flip-flop inputs here ones and here ones. In between, how many number of times J and K value was changes, and whatever those values are, my output was fixed. Let it be see here, friends, if it is a positive edge triggering, here I should consider what my flip-flop inputs are. At this incident, I identify that J is equal to 0 and K equal to 1, and my Q output is 0. That means this whole duration Q output is equal to 0. It is not races between 1 and 0 or 0 and 1. The next clock pulse, again, we are coming only this side. That time, again, I'll go and check what J and K value. The time J is equal to 1, K equal to 0, then my Q value is changing from 0 to 1. Like that, I can overcome this race around condition by using edge triggering. That means only at this edge or this edge of the clock pulse, your flip-flop can accept J and K inputs. According to that one only, it can produce an output. So that's what I mentioned here. The second thing is master-slave configuration. In this master-slave configuration, the name itself indicates there are two flip-flops are merged internal to a flip-flop structure. One is act as a master and another one is act as a slave. The output of master is given to the slave and output of the slave is given to the input of a master. And basically we are applying the inputs to the master flip-flop and output we are considering from the output of slave flip-flop. And here important thing is, at a time these two flip-flops are not active simultaneously. Because we are applying common clock to both, but clock is directly applied to the master flip-flop. And but for the slave, we are applying clock pulse through an OR gate. So that master and slave both are not active simultaneously. If the inputs are applied to your flip-flop, that time master is only active, slave is inactive, so that output we are not getting. And the next case, your slave should be active, master should be off. The time the output produced by the flip-flop, that is again, if you cut back to the input, no issue because your master is not active. So that is an idea here we should follow in this master-slave configuration. If it is over one clock period, then the race around condition can be eliminated. This can be done by using master-slave ZK flip-flop. See here, friends, this is that structure is. We know that clock is nothing but we have on period as well as off period. That is a complete clock cycle duration. In case of on period and off period, in case of on period like this, your clock is this. From this end to this end, we have one complete clock cycle. So in this duration, how your flip-flop output can be get? Here the clock is directly applied to master flip-flop, and the clock is applied through a NOT gate for the slave flip-flop. Let it be here I was applying J and K input, and this input and this input was readily available. If I apply clock pulse and this master is active, here the clock is 1, the output of inverter becomes 0, so that is applied to the clock input of slave flip-flop, so slave flip-flop is not active. Even though we have an output, we are getting at the output of this, those are not accepted by the slave for the duration of this, because up to this your clock is 1. Next clock value becomes 0. Once it is 0, then this master flip-flop is off, this was off, but this slave flip-flop is on. Because 0 passes through this NOT gate, it becomes 1, then the slave is on, and the slave will accept the inputs which are produced by the master, and according to that it will produce as an output. Even though this output we are applying to the input of the master, but it can't accept. Why? Because your master is off for complete this duration of period. So that means one complete clock cycle, that is from this period to this period, we have only one value that should be present at output of the flip-flop. So it should be constant. So this is the way how we are going to eliminate a race around conditions in case of master slave flip-flop. Okay, so we can overcome this race around condition by using master slave configuration or edge triggering notation in case of JK flip-flop. I hope you understood what I was discussed. So under this particular concept. Thank you for patient listening. We'll meet on next class to discuss another topic. Thank you.